Hi, Real. Hey, how's it going? I guess not.
Thank you. That's
There you go. Yeah, I guess so. Hey.
For some reason, I thought your office hours today were at 1.
Oh, those are on Wednesday.
So I came to school.
I'm usually in my office around that time though. So if my door is closed, you can knock And
I
from
know,
there,
I don't think you were there though.
oh, okay, I see. Oh, yeah, I was out to lunch at 1 o'clock.
Yeah, so I'm gonna struggle with my cooking work instead.
Mm. All right, it's 4 o'clock, so let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? Good, good. Hopefully everyone had a good weekend. And so this is we're gonna have 2 full lectures this week, so it's not a short week. So I finished grading your homework ones, and so your grades for those should be on Canvas. So if you turned it in physically, I have it here for you, so you can pick it up after the class. But even if you turned it in physically, I gave you feedback on Canvas as well. And so you should see some comments on your assignment. And so you have feedback on your written assignment and also on Canvas. Okay. And so remember, homework 2 is out there right now. And so that's going to be due, I think, next Monday. I think that's the due date for that. Okay, so make sure you're working on that. And if you have any questions on that, definitely let me know. Okay, so the plan for today is we're going to continue on with our lecture notes about bones. Okay? And so today I anticipate we'll get through the second half of the lecture notes. Hopefully finish it up. Okay. And then on Wednesday, we're going to start talking about muscles. Okay. All right. So there are any questions I can answer before we get started today? Okay. All right. So let's go ahead and get started. All right. So where we left off on last Wednesday was we were talking about the elastic properties of bones. And by this, and so what I mean by this is, we want to characterize how bones behave as a material. Okay. Because in engineering, specifically in mechanical engineering and civil engineering, we work with a lot of different materials, right? So we work with a lot of metals, a lot of concretes, a lot of woods, right? And a lot of times, in order for us to do our engineering work, we have to have an understanding for how those materials behave, right? And so usually we're looking at things like the Young's modulus, we're looking at things like the density and the Poisson's ratio for these materials, okay? Okay. And so a lot of the engineering materials that we use are characterized in terms of these, but bones are a lot more complex material, right? And so we talked about last time that bones are, chemically, are composed of things like calciums and, calcium carbonates, things like water, things like collagen, right? But we also learned that bones also, can be porous as well, right? And so there's a significant amount of bone that has lots of holes or lots of pores in them, right? And that affects its material properties, right? And so bone can't strictly be characterized by just its Young's modulus or a single Young's modulus in the Poisson's ratio. Okay? In particular, bones have this very distinctive characteristic that they're much stronger in certain when you load them in certain directions. Okay, and in particular, bones are much stronger when you load them in compression and tension rather than shear. Okay. And so our material model, or how we describe these bone materials, has to kind of reflect this. Okay? And so instead of being an isotropic material, what we said was that bones are often characterized as, generally as an anisotropic material, but more specifically, we were looking at two different material models for bones. Okay? One was SPAM. The other one was called a transversely isotropic. And the other one that we'll go over later in a bit is called orthotropic. Someone really wants to talk to me now. Let me put my phone on silent. Sorry about that, everybody. Okay. And so orthotropic is the one that I want to focus on because this is one that's often used in mechanical engineering. Okay. And so orthotropic, an orthotropic material model, this is often used to describe the material properties of wood. Okay. And so, we'll talk about this later on where comparing bones to wood isn't the most perfect, analogy, but they share a lot of the same characteristics. Okay? Because the thing with wood is that woods often have a fiber or a grain that runs through them, right? And the direction of that fiber or grain, has a big impact on its material properties. And so if we think of bones as kind of the same thing, then, we can, that gives us a pretty decent material model for bones. Okay? All right. And the way we're going to describe these material properties is using the following relationship. Because when I talk about material model, we're often talking about the relationship between stress and strain in the material. Okay? And so normally, for an isotropic material, we just have the relationship between stress and strain as just the Young's modulus, right? And so we would have E right here in between the equal sign and the epsilon. But for an anisotropic material, we would have some matrix here of material constant Cij. Okay? Where the Cij right here, this is a matrix of material constants. Okay? And in particular, it's a 6x6 matrix. Okay? And so in the worst case, you can have up to 36 different kinds of material constants that you could use to describe the materials. But oftentimes, we make assumptions in order to cut that number down. Okay? And so last time, we went over transversely isotropic. And so this had 5 material constants. Okay? Right, just kind of based on the symmetry assumptions that we're making. And what we'll see today for orthotropic, it's going to be a little bit more complex. But also it's going to give us a little bit of a more holistic picture of the bone material properties. And this one will have 9. Okay. Okay. And so on the next page, I'll show you the structure of the Cij matrix for an orthotropic material. And then I'll give you some typical values for bones based on some experimental measurements. Okay. All right. Any questions on this so far? This is kind of just a little bit of review from last week. Okay. All right, so let's look at what the material constant matrix looks like for an orthotropic material. Remember, keeping in mind that this is what's often used to describe the material properties of wood. Okay, so for an orthotropic material, our CIJ looks like the following. Okay, so we have C11, C12, C13, okay? And then we have zeros for the rest of the first row. C12, C22, C23, 0, 0, 0, C13, C23, C33, 0, 0, 0. And we have 0, 0, 0, C4, 4, 0, 0, 0, 0, 0, 0, C5, 5, 0, and then 0, 0, 0, 0, 0, C6, 6. Okay. And so if you count the number of unique entries here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I double counted this one. And so there should be 9 of them, right? So we have all of the top, the diagonal entries, and then the kind of the top, the upper, above the upper diagonal for the top left portion. Okay. We have 9 unique constants. Okay. All right, and so let's talk about some measurements that people have taken. Okay, and so I'm going to give you 3 different experiments that people have done that measure these quantities. Okay, and then we'll talk about what some of these values actually mean. So let me go ahead and make a table. And so we have C11, C22, C33. Okay. We have C44, C55, C66. Okay. And then I'll list all the off-diagonal ones on the next page. And so for this first experiment, this was done by a researcher named Van Buskert, right? And so he actually did measurements on a pig femur. Okay. So not human, but usually it's a lot easier to do experiments with non-humans, just because it's less ethical things to jump through. Okay. Remember, the femur is the big bone that's in your thigh. Okay. So this is basically a pig thigh right here. Okay. Next, we have measurements on a human tibia. Okay. And then the last one here, we have measurements on a human femur. Okay. Okay. And so let's go ahead and start filling in some of these values. And so for a pig femur, we have, this is going to be 14.1. Okay. For the human tibia, this is going to be 11.6. And then for the human femur, this is 20.0. Okay. And so all of these numbers in this table right here are given in gigapascals. Okay. So that's the units for everything in this table. Okay, and so for C22, we have 18.4, we have 14.4, and then 21.7, okay? Then for C33, we have 25.0, 22.5, 30.0, okay? All right, so I'll have you guys write that down, and then we'll talk about these numbers in just a second, because right now these I think it's a little bit hard to kind of gain appreciation for these numbers just because they're just kind of numbers in a table. But let me go ahead and draw a bone up here just to kind of show you, what these mean. Okay. All right, so what I want to draw your guys' attention to is I want you to notice that C33 here, or the the C33, this one is the largest value, and it's used, and it's by a significant margin too across all 3. So the way that this number 3 direction is defined is this is the direction that's down the shaft of a bone. Okay, so if you consider a typical long bone, the 3 direction is going to be down the shaft. Okay. Okay. And so it makes sense that this material property here, this constant is the largest, because we know that bones are the strongest whenever they're loaded in compression and tension. Okay. Meanwhile, if you load them, also as a normal force, in the 1 or 2 directions, you can see that it's not as strong, but still, fairly strong. Okay. And so the values for C11, C22, they're fairly comparable, but you get a little bit more, you get a little bit more strength in the kind of the transverse direction, going one way versus the other way. Okay? All right, so now let's fill in the values for C44, C55, C66. So this is going to be 7.0. Next is going to be 6.3, 5.28. Okay. 4.91, 3.56, 2.41, okay. 6.56, 5.85, and then 4.74. Okay. All right. And so for all of these constants here, you can see these are a lot lower than all the other ones, okay? Because what these represent the strength of the bone in shear. And so C44, C55, C56, that determines, the strength of the bone when you're shearing in, in this direction versus this direction and this direction, okay? And so you can see here, these are a lot weaker. So this kind of confirms, what we said before, that bones are a lot weaker in shear than they are in tension or compression, okay? Okay. Any questions on this so far? Okay. All right, so let's go ahead and fill in the rest of the values for C11 or C12, C13, and C23, because that's the, those are the last ones that we didn't have here. We have C12, C13, and C23. And so our first row here, that's going to be our pig femur, just like before. Then we have our human tibia. Okay. And also human femur. All right. And so you'll see for all of these, they're also very low values as well. Okay. Right. And so these, what these material constants tell you is how strong, the material is in, when you compare, the normal a load in the normal direction, but its effect on a different direction. So these also are kind of an expression of kind of shear strength in the bone. Their exact definition is a little bit different from the C4s and C5s that we talked about on the previous page, but these are also kind of a measure of shear. And so you can see here that these values are kind of on the same level as C44, C55, C66. Okay. And so again, these kind of show that bones are a lot weaker in shear. Okay. And so, another thing I want to highlight about this data is that they just kind of represent one experiment's worth of data. Okay. And so the thing about bones is that getting accurate measurements of bone strength is still kind of a very hot topic of research right now. So, these people were able to kind of do it, with the force meter, but it's still, something that's difficult, right? Remember we said last time that water makes up a big part of a bone structure, right? And so if you just simply take a bone out of a cadaver, unless that person just very recently passed away, the bone is going to very naturally dehydrate, and it's hard to kind of get that exact composition of water that it has in the body. Okay, and so coming up with ways to measure these material properties is still like, people are coming up with lots of crazy things like using ultrasound. Or come up with ways to kind of effectively rehydrate the bone. So it's still, still an ongoing area of research. But these values here kind of give you a good starting point on which you can do some analysis. Okay. And these three aren't the only ones too. And so I kind of picked these three from kind of a huge list of experiments, just to kind of illustrate to you that even between bones and this within the so if you look at the human tibia and the human femur, you still see some variation, right? Because those two bones, they kind of vary in size and they vary in composition as well. So, what I would expect is that the femur is expected to be a lot stronger because that's your only thigh bone. Whereas the tibia, that's one of the two bones in your lower leg. And so it can be a little bit smaller and a little bit weaker because it also has the fibula there to kind of help share some of that load, okay? But, and of course, across different species, you expect to have different material properties, and a lot of it depends on how porous the bones are and what its exact chemical composition is. Okay. But just know that there's literally hundreds of these kinds of experiments out there. So, I picked three just because I think these three kind of tell a good story together. But if you kind of search it up in the literature, you'll find tons and tons of different experiments that people have. Okay, so any questions on this? Okay.
Is that a like fracturing point of the bone or just the safety amount that can be applied?
Yeah, it's a good question. So the question is, are these the fracture points of the bone, or do they, or do they measure how much load that they can take in? So all of these constants represent is essentially like the Young's modulus, and so the Young's modulus basically tells you if you apply this much stress onto a material, how much strain or how much deformation you can get. And so these constants are basically the modifier for, if you apply a certain load, how much deformation can you get? Yeah. So the ones with higher constants will tell you that it can withstand higher loads and higher stresses before it starts to actually deform. Yeah. Mm-hmm.
Is it in certain directions?
All right. Any other questions on this? Okay. Okay. And so remember, so these constants here are for an orthotropic material. Okay. Okay. Remember, orthotropic is often the material model that we use for wood. Okay. And so this works great for wood because wood, you have a very defined, fiber that you can just follow. And then what you can do for wood is you can say that, my fiber direction is going to be the same as the 3 direction. Okay. And you can imagine this working well for the long bones because long bones have a very pronounced kind of axis in which you can define it, right? But there's a lot of bones in your body that don't have kind of a clearly defined axis, right? And so like let's take, for example, some of the bones in your spine, right? And so your vertebral bones are kind of these like cylindrical, cuboidal looking things, right? And so that's a very poor picture of that. But you can see from these bones, right? We know just from just from biomechanics that the vertebrae are often loaded in compression like this, right? And so you can imagine other vertebrae that are above or below it that kind of compress it like that, okay? And so you can argue that, we can set this to be the 3 direction here, okay? And so, you can do that, but it doesn't have a distinct shape. It doesn't have a distinct shape, and it doesn't have like a distinct, axis, or, it's not obvious a lot of times where we can choose which direction to do this. And so for bones, even though the orthotropic material model works pretty well in some cases, for some of the more awkward shaped bones, it's a little bit hard to determine, which direction works well. And even if, this model is a good model for those ones, okay? And so there's limitations to this as well, right? And so that's kind of what I wanted to illustrate to you guys. Okay, any questions on this? Okay. All right, and so speaking of bone shapes, let's go over some of the different ones that are out there, just really quickly, and just talk about some of their quotes. Okay. Because often when we think of bones, we think of like the long bone, and so those are the ones that are kind of easiest to draw. But in reality, you have a lot more kinds of bones in your body that all serve different purposes. All right, and so let's go over, first let's go over the short bone first. The opposite of a long bone. Okay. And so short bones, these are, they come in, lots of different shapes, sizes, but approximately you can kind of think of them like a cube. Okay. Okay. And so, when I say it's cuboidal in shape, I don't actually mean to look like a cube, but what I mean is that its form factor is approximately the same lengths in each direction, right? Okay. And so some of the most prominent examples of short bones in your body are in your hands and feet. Okay. Okay. And their structure basically allows them to glide past each other really easily. Okay. And they also are great at shock absorption too. Right. And so I have a very poorly drawn example here. So when I was writing my notes, I was looking at an image from Google, okay, and I tried to transcribe that, and it turned out terribly. And so now I'm going to do a transcription of a transcription. So I'll do my best here. Okay, so if you look at kind of the bones that make up your hand, you kind of look at an X-ray like this, you'll see that your hand is kind of composed of a lot of these kind of almost cuboidal looking bones that kind of form form that shape. Okay. Okay. And then from here you have your finger bones. Okay. And so this right here would be a short bone. And so here would be your fingers. Right, so you don't have too many of these types of bones in your body, but they are in places when you need some kind of gliding motion. Okay, any questions on torque bones? Okay. All right, so that's the first shape. Okay. The next shape that we'll go over are flat bones. Okay. And so flat bones, the way these are shaped is that they kind of have a flat kind of sheet-like shape. Okay. Okay. And so in other words, they have kind of a thickness to them that's very thin, but the other two dimensions are pretty big. Okay. And what these are for are they're mainly used for protecting any kind of organs or soft tissue underneath. Okay. Okay. Another nice thing about flat bones is that they provide a very nice large area for muscles to attach. Okay. Okay. And so whenever you have a joint in your body that allows for very complex motion, like your shoulder joint or your hip joint, you'll often see a flat bone there because in order to do any kind of complex motion, you need to be able to attach to a lot of different muscles. And kind of the large surface area of these muscles allows for that. Okay. Okay, some examples that you'll see in your body. The one that I'll draw below here is your scapula. Okay. Okay. And so if you're if you kind of remember from before, your scapula is your shoulder blade bone. Okay. Right. And so your shoulder, kind of we talked about before, is one of the ball and socket joints in your body. And so because its motion is so complex, right, you can do lots of different things with your shoulder. You need a very large kind of a large surface area bone in order for all the muscles there to attach to. Okay. So some other examples are your sternum. So that's right in the middle of your ribs. Okay. The ribs themselves. Okay. And also the patella. Okay. And so the patella is your knee. Okay. And so to draw an example, let me draw the scapula. And so your shoulder blade bone kind of looks like the following. Okay. So again, a terrible drawing, but hopefully it gets the point across, right? And so you kind of have a large flat surface over here. Okay. And so underneath this the shoulder blade here, you have a lot of the muscles that compose your shoulder. Okay. And there's a lot of places where your muscle can attach to, right? And so if you think back to homework 1, right? So homework 1, I had to do kind of a static analysis of a shoulder, right? And so at that shoulder joint, we had just so many muscles that are coming in and acting on it, right? And so you can have a muscle acting this way, this way, this way, this way, right? And so you have lots of different places where muscles can attach to and perform all different kinds of motions just because of its large surface area. Okay. Okay, so any questions on this? Okay. All right. Next, we have irregular bones. Okay. And so irregular bones is kind of like the miscellaneous category, right? And so all bones in your body that don't really fit into any of these any of these other categories, we kind of just group them in here. Okay. Right, and so the exact definition of irregular bones that they have a very specialized shape to fill a specialized role. Okay. Right, so some examples that you'll see are things like your vertebrae. Okay, so your vertebrate bones are actually, kind of cuboidal in shape, and so you can kind of make the argument that they're short bones. But your vertebrae also have kind of the inside of it is hollow for the spinal cord to go through, and it also has these kind of appendages that come off the outside to kind of prevent certain motions as well. And so they're technically classified as irregular bones. Okay. So some other examples could be like the sacrum of your pelvis, right? Or your hip, and also the coccyx of your hip as well. Okay, coccyx is your tailbone. Okay. And so since the irregular bones, they all kind of have their own unique shape. I'm not going to attempt to draw them, but any bone that doesn't fit into these molds, you can consider them. All right, and so the last type of bone that we'll go over is the one that we've been talking about the most, and these are your long bones. Okay. And so the long bones, they have a slender, long cylindrical shape. Okay. Okay. And their main purpose is to kind of form the structure for your limbs and appendages. Okay. And so inside your arms and your legs, those are all long bones. Okay. And so this is an example of a long bone. Okay, and so this could be like your femur. Okay, femur is the biggest long bone in your body. Okay, but also you have your humerus in your arm. You have your radius, your ulna in your arm, and your tibia and your fibula are also examples of these long bones. And so, just like how each of your different limbs, they kind of vary in size and shape, these long bones could also vary in size and shape as well. Okay. All right. Any questions on any of this so far? Fairly straightforward. Good. And so kind of the distinction that I want you guys to remember is kind of, going from short bones to flat bones to long bones. Okay. Because if you think of like a short bone here, right? And if we think of, our three cardinal directions here, so X, Y, and Z, right? Like a short bone will look something like this, right? So we approximately said it's cuboidal in shape. Okay. And so if we measure the short bone in the X direction, okay, and so we call this maybe the X form factor, maybe this is the Y form factor, and then going into the page Z, okay. Okay. For short bones, all of these lengths will be approximately the same, right? And so the X length will be approximately equal to the Y length, which is approximately equal to the Z, okay. Right? And so that's what makes them short bones, is that if you kind of measure the bone in kind of any direction, you'll get something that's pretty similar. Okay. Whereas for a flat bone, right? If we do kind of the same thing, if we measure something in the X direction, okay, so we'll call this length in the X versus length in the Y direction versus length in the Z, okay? The characteristic for a flat bone is that one of these lengths is going to be much smaller than the other, okay? So that's kind of what makes it flat. And whatever the shortest dimension is, that's going to be the thickness of your flat bone, okay? And that determines a lot of the properties. And then if you do the same thing for a long bone, right? And so we consider LX versus LY versus LZ, okay? Right, and so for a long bone, one of these will be longer than the other one because that's kind of the dominant direction. Okay. And so if you make the comparison to like a mechanical engineering situation, right? Your flat bones will be kind of like your sheet types of material, right? And so if you have sheet metal, you know that for a piece of sheet metal, in the dimensions of the, two of the dimensions are going to be much bigger than the other one. And so the last one being the thickness of your sheet or your plate. Okay. And then your long bones here, those would be like your beam type of structures where, the length of the beam is really long, but then the depth and the height of the beam, the other two dimensions are going to be really short. Okay. And so they serve a lot of the similar purposes as those kinds of structures. Okay. And so if you think of, mechanically of, what's the purpose of a, of a beam or a rod inside your mechanical devices versus the purpose of a sheet versus the purpose of, maybe a cuboidal structure inside your mechanical device. I think that's kind of the right thinking to think about for, the purposes for the various shapes of these bones. All right, any questions on these? Okay. All right, and so that's, bone geometry. So let's talk about how bones grow and develop. Okay. And so unlike, unlike mechanical materials that we're used to working with, bone is actually living tissue. And so bone will actually grow and develop along with the person. If you think back to, how big your bones were when you're kind of a little toddler versus, how big you are now, so that's only accomplished if your bones are able to grow, right? Okay. But bones can actually also deteriorate. Okay, so generally, as people age, once you kind of get past your growth period as a person, your bones will actually lose strength and density. And so it's actually a very dynamic tissue that I think people kind of take for granted. And so just like, any other part of your body, you have to take care of your bones, right? Otherwise, it could be, pretty bad for you later on in your life. Okay. Right. And so how do bones grow? So bones can grow kind of in two different ways. Okay. Okay. And so the first way, and this is kind of most prominent when people are still kind of, growing, is is longitudinal growth. Okay. And so in other words, longitudinal growth just means that the bones are getting longer. Okay. Right. Another way that they can grow is circumferentially. Okay. And what this, all this basically means that the bones are going to get wider. Okay. All right, let's talk about longitudinal growth first. And so longitudinal growth occurs at a specific place in your bone called the epiphyseal plate. Okay. And so the epiphyseal plate is basically a disc of cartilage that's that's present at the very ends of bones. Okay. Right. And so when your bone grows longitudinally, what's happening is that at the epiphyseal plate, then basically new bone cells are created, okay? And then these are kind of added to the bone to kind of make them. Okay. And so if I draw kind of a stereotypical long bone here, okay, the epiphyseal disc or the epiphyseal plate is approximately kind of near the end. And so it's not quite at the very end because at the very end, that's where the bone kind of contacts other bones. And so that needs to be kind of strong. But right past that part where the bone, right past the joint, that's where, new bone cells are at. Okay. And so typically, for most people, the epiphyseal plate is most active during adolescence. So that's when you're kind of still growing as a person. But once you kind of get past a certain age, then the epiphyseal plate tends to disappear and tend to kind of just degenerate away. Okay. And so the point at which this fades away is different for every single person. But typically it occurs when between the ages of 18 and 25. Okay. Right, and that's around the time that people, that we kind of generally expect that people will stop growing. Okay. I knew that when I was age 25 and I still wasn't taller than my dad, then it's just not going to happen. My dad's always going to be taller than me. Okay. Any questions on this so far? Okay. All right. So now let's talk about circumferential growth. Okay. And so unlike longitudinal growth, be smart. Good luck. Best of luck on that. Right. And so unlike longitudinal growth, circumferential growth can actually happen all throughout a person's life. Okay. Oh, it happened really early for you. Right. And so, even after you kind of stop growing, in terms of height, right? your bones can actually still get wider, okay? And the main reason for this is that, as your bone gets, as you kind of, get older and older and you place kind of more weight on your bones, sometimes the bones still need to adapt in order to carry that weight, okay? Because as people tend to get older, they also tend to get, a little bit more overweight, okay? Especially in America. And so in order to kind of account for that, then, your bones can still kind of grow wider, okay? But with that said, once you kind of get past that age of whenever you stop growing, this process slows down significantly, okay? And so even though it's still possible once you're older than, 18 or 25, it's a lot slower then. Okay. And so most of your growth is going to happen in your adolescence. Okay. Right. So for some of you, some of you, I think you still have some time in order to keep growing, but then, for a lot of us, we're kind of past that. Okay. Okay. All right. And so that's bone growth. Okay. But in addition to that, bones can still, their composition still changes over time. Okay. And in particular, one of the processes that happens as people age is that your bones will start to lose collagen. Okay. And if you remember from last time, collagen is like this this kind of like fibrous material that comprises a lot of your tissues. And what collagen gives your bones is a kind of a way to be flexible. Okay. And so the fact that your bones, the fact that your bones have a little bit of play in them, that you can kind of bend them, is thanks to collagen, right? But as people age, the collagen in your bones gets less and less, and the net effect of that is that your bones become more brittle. Okay. Right. Additionally, in addition to losing collagen, your bones actually start to lose some important minerals as well. Okay. Okay. And so, in addition to becoming more brittle, your bones start to lose strength and and density as people age as well. Okay. Okay. And so later on, we'll talk about a specific condition which, where people tend to lose a lot of minerals at an alarming rate called osteoporosis. Okay. But even without osteoporosis, people can still lose, significant minerals within their bones. Okay. Unfortunately, this effect is a lot more pronounced in women. Okay. And so for women, people have measured that they typically lose about 0.5 to 1% bone mass per year, okay, once they reach kind of adulthood. Okay. And once they hit menopause, it actually becomes a lot more pronounced. And so after menopause, the average is about 6.5% bone mass per year. I distinctly remember growing up that my mom had these like calcium chocolates that she would eat every day. And I thought she was just eating candy. And so there's one time I just went into her stash and just ate a bunch of them. And she got really mad at me because, those are keeping her bones healthy. But I had a ton of calcium for one day, and they were tasty chocolates. Okay, so any questions on this? All right. And so now let's talk about how bones respond to stress. Okay. Okay. And so, just like we just finished talking about, bone is a living tissue in your body. Okay. Okay. And so the bones could actually sense, all the stress and all the loads that are placed on it. Okay. Right, the cells inside your bones can they kind of all they do a lot of things, but one of their functions that they kind of act as mini force sensors within your body. And because of this, because they can sense these stresses, they can actually respond to them and kind of alter their size and shape and chemical composition in order to best react to them. Okay. 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 And so when does this mostly take place? Okay. Or why is this important? Okay. And so this kind of follows the kind of general principle of within your body that was first coined by a guy named Wolff, that form follows function. Okay. And so that might have been a phrase that you've heard before. Okay. And so this phrase is attributed to a researcher named Wolff. Okay. And it's known as Wolff's law. Okay. And what that basically says is that when you look at the size and structure of tissues and the shapes of tissues in your body, right? Their size and shape have been designed very kind of intentionally, right? And that's with the intent that they kind of best serve the purpose in which they're made for. Okay. And so your long bones have their specific shape and their specific size, specifically to act as good places for your limbs. Okay. Whereas your vertebrae bones, they have a specific size and shape that kind of makes it best for handling the loads of your weight. Okay. And the thing or the process, the biological process that actually drives this form follows function law is the fact that bones could actually sense and respond to stresses. Okay. Because you can almost think of this response to stress as kind of like a correcting behavior. Okay. And so if your bones kind of sense a certain kind of stress or a certain kind of load, what it does is it kind of alters its shape and it alters its size such that it can better handle those kinds of loads in the future. Okay. Okay. And so I'll give you kind of the biggest example here. Okay. And so let's talk about, exercise. Okay. And so when you exercise, certain kinds of exercise are more effective than others, but, in general, exercise, what it does is that it places kind of unnaturally high loads on your bones. Okay? And so what I mean by that is, it places loads and stresses on your bones that you wouldn't get if you were just kind of sitting around on the couch. Okay? Okay. And so in response to exercise, especially if you do this regularly, your bones are going to get stronger. Okay. It's something that's kind of said in a lot of, advertising for, trying to get kids to exercise, but it's true. Okay. Okay. And so kind of, microscopically, what's happening is that when you place these stresses and loads on these bones, is that your bone cells kind of sense this and say, hey, we're feeling a lot of stress from this activity. Maybe we should make ourselves stronger in case, a bigger force comes later on, right? And so, regular physical activity, of course, it's important in order to kind of keep in shape, but it's also really important for your bone health too, because it kind of encourages your bones to kind of stay strong, right? Because if you live a sedentary lifestyle and you kind of just sit on your butt all day and kind of just don't exercise, then your bones are like, hey, we're not really feeling any kind of stress, and so we can kind of we can kind of become lighter and kind of take some of that strength away because this person is not going to need it. Okay, and so that's why they tell you that if you don't really exercise all that much, don't really push yourself super hard, because if you try to lift a ton of weights, they always tell you you're going to put yourself at risk for injury, right? And there's a lot of different ways that you can injure yourself, putting yourself under extreme load. But one of the ways is that your bones are going to be weaker than someone who exercises regularly. Okay. Right. And so this process through which bones kind of improve themselves, over time, or they kind of respond to stress, is called remodeling. Bones aren't the only tissues that can remodel in your body, and so that's why I kind of denote it as bone remodeling here. Okay? And so remodeling is kind of a general term that can be used for any kind of living tissue. Okay, but basically what's happening is that during remodeling is that older, more damaged bone material is reabsorbed. Okay. And by reabsorb, what I mean is that these materials are kind of taken into your bloodstream and they kind of get ejected out, ejected out from your body. Okay, and then these damaged older materials are replaced by newer, stronger bone materials. Okay. Yes, yes. Yeah, so Samson makes a great point in the chat. And so, whenever you have an injury to your bone, physical therapy is something that doctors will often recommend, right? And the point of physical therapy is to kind of give your bones kind of, a taste of what it is to kind of be under stress again, to help it, remodel correctly and heal appropriately. Okay. And so if you've ever undergone physical therapy before, it's basically a lot of, relatively light exercises that kind of ramp up over time, right? And the process, and the point of that is, as Samson was saying, is to kind of, make sure that the bones, remodel properly and give you kind of the old strength and the old properties that it used to. Okay. Okay, so any questions on this?
So is it like weight bearing exercise or any exercise?
Yeah, that's a great question. So the question is, is weight bearing or any kind of exercise? So any kind of exercise will help to trigger this process, but weight bearing exercises are much better for this. Yeah. And so if you're kind of regularly lifting heavy weights, then that's gonna put more stress on your bones. It's gonna trigger much more remodeling than that. Mhm. Yes, yeah. Yeah, so if you injure your legs, yeah, weight bearing isn't recommended. So there's usually a ramp to this. And so, if you're injured, of course, you don't want to re-injure yourself by lifting heavy weights. But for a normal kind of healthy person, if you do weight bearing exercises, then it can help encourage healthy remodeling in your bones. Yeah. Mhm.
And then in the remodeling process, I know like when you work on weights, you tear your muscles slightly and that's why they get bigger. Are you creating like micro fractures in your bones as well?
Yep.
That replace like just replace with calcium?
Yep, that's exactly what you're doing. Yeah, so I think people kind of are familiar with that process with muscles, and that's how muscles get bigger. But it also occurs on a similar scale for your bones too. But the thing with your bones is that they don't normally get bigger or noticeably bigger. They just kind of get replaced by stronger, healthier bones.
Oh.
Yeah. Mhm. Right. So any other questions on this? Okay, and so that's remodeling, but bone modeling can also take place. Okay. And so all bone modeling is your body triggers the creation of new bone, but without the reabsorption of old bone. Okay. Okay. And so this is a process. So bone modeling often takes place for for adolescents or for those people that are still growing very rapidly. Okay. Okay. All right. And so even if you're not, even if you kind of have reached the point where you've kind of stopped growing, regular exercise is still really important. Okay. And so not only for the obvious other benefits, but it kind of keeps your bones stressed. Okay. Because if your bones actually don't trigger enough stress to trigger remodeling, what happens is that your bones will start to reabsorb kind of the older kind of damaged tissues, but it won't replace it with newer ones. So there's a question in the chat. So is that like bone spurs? Bone spurs is something a little bit different. So this is kind of a more kind of natural process. Bone spurs is a specific kind of incidence that can occur for certain individuals. Yeah. Mhm. Okay. And so basically all throughout your life, there's a lot of benefits to regular exercise. Okay. One of which is making sure that your bones are healthy. Okay. All right. And so this was kind of already answered in a question, but if you're following along in the notes, high intensity exercises are a lot more effective at triggering bone remodeling. Okay. Okay. But any kind of exercise works, right? So even just walking, right? And so by walking from one place to another, you actually are putting a decent amount of stress on your bones, and that stress coming from gravity, right? And so even just supporting your own weight is an important part for keeping yourself healthy. Okay? But if you can do it, any kind of weight bearing exercise or high intensity exercise will be kind of most effective at doing this. Because for most people, just the act of bearing your own weight is something that's important for bone health. Okay? Okay. An interesting thing kind of happens for astronauts actually. So, that's not going to affect the vast majority of people, at least not yet, unless we figure out space travel. But for astronauts, they go into an environment that's low on gravity. Okay? And so what can happen is that their bones will actually start to deteriorate very quickly, compared to people on Earth, because they don't have the stresses that are associated with weight bearing. Right? And so, monitoring that health for the bone health for astronauts, especially the ones that spend any significant time in space, is something that's really, really important. Okay. And so actually, because astronauts don't have that weight bearing that people on Earth do, astronauts can lose up to 1 to 3% of bone mass per month. Okay. Because if you remember, we talked about earlier that, women can lose, 0.5 to 1% bone mass per year, and that's a significant problem. And so you can imagine losing, 1 to 3% bone mass per month. And so that's going to be a much, much bigger problem. Astronaut hamster wheel. Yeah, it's any kind of exercise that you do up there is going to be effective, although it's going to be a lot harder because, I think we underestimate just how much just gravity kind of helps us, maintain our health and gives us, a lot of stress on our bones. Okay. All right. Okay. So any questions on this?
Yeah, so but for exercise, in terms of exercise, like you can't do any weight bearing exercise in space. You have to do like tension based
Yes.
machines.
Mm-hmm.
But does that even have the same effect as like in terms of like bone health?
It's hard. It's like,
like, like if you're holding like a bench press or a dumbbell on your arm, you could kind of picture how that would have a direct like force relationship on your bone. But if you're like pressing something that's like all the resistance is coming from tension-based forces, does it even do the same thing?
Yeah, so it's definitely a lot more difficult. So anything that requires any kind of weights, you can't do that in space because weights require gravity. But you can do isometric stuff, and so you can have your muscles kind of push against each other. Okay. And so that's one thing that you can do in space. They probably might have developed other techniques and other machines that can help you exercise isometrically without weights. But it's hard. So even with those exercises, nothing is going to be as effective as like you doing weight bearing or weight or any kind of weightlifting with gravity. And so, even with those exercises, I think astronauts still lose a significant amount of health. Yeah. Mm-hmm. Yeah. Good question. Okay. And so we're almost out of time for today, but I do want to give you a couple more vocab words just to, before we go. Okay. And so the first one, and so these are kind of opposites to each other. And so the first one is bone hypertrophy. And so the key word here is hyper. Okay. And so when you think of something that's hyper, you think of something that's kind of, very, beyond kind of what's normal. Okay. And so bone hypertrophy happens when your bones are exposed to higher and more frequent states of stress. Okay. Right, in these situations, what you can have is you can have the bone actually trigger, much higher growth than normal. Okay. Okay. And so these are cases, these are usually used to describe cases where one bone is kind of abnormally big, a certain individual compared to something else. Okay. And usually this occurs a lot in a lot of the long bones. Okay. And so some of the examples where you see it most often are actually often in athletes that use kind of one limb or one muscle more than the other. Okay. And so what's most common is that you see these in like the arms of a baseball pitcher or maybe a tennis player. Because in those sports, you kind of expose one arm of your body to a lot more stress than the other one. And so a lot of times if you compare kind of the bone mass and the bone size for one of the arms, the one that's used for the action versus the other one, one is going to be much bigger and much more dense than the other one. And the last one that I'll leave you with is kind of the opposite, which is bone atrophy. Okay. And so bone atrophy is when a bone loses calcium and mechanical strength due to lack of stresses. Okay. Right, and we've already talked about kind of all the factors that can trigger bone atrophy. So if you have like a sedentary lifestyle, right, whether through just laziness or maybe you're bedridden or a senior citizen, okay, or maybe you're an astronaut and you go through space and you just don't expose your bones to any kind of really very stresses. Okay, and so whenever your bone kind of loses mass, we call that bone atrophy. Okay, any final questions on this before we wrap up for today? Okay, all right, so that's all we got time for today. And so thank you guys for tuning in, right? And so we'll pick this up on Wednesday and we'll finish up these lecture notes on bones and then we'll start on the muscles, right? So have a great afternoon, everyone. Stay safe out there and I'll see you on Wednesday. Thanks, everybody.
Professor, so for the bike tank thing in our FBA class, so I misread it. And the refinement took my model from, it wasn't 23,000, it was 230,000 units.
Oh, man.
So I couldn't change anything at home. You were right. It doesn't allow me on the student version to do any type of analysis over 50,000. So I kind of just answered what I could. And then are you going to let us stay afterwards today to? Oh, yeah. Are you going to let us stay afterwards today to like do it and everything? Oh, yeah. I mean, every day you can stay after. I don't mind. Okay. The only thing is that, just turn off the lights and, and put the recorders. So. Okay, yeah, because I can't make any modifications on the ANSYS student.